The S-block elements include all the elements of Group 1 and Group 2 of the periodic table. Although these two groups are different in many ways, they also share several important physical and chemical properties because they both belong to the S-block. The reason for these similarities is that their outermost electrons occupy the s orbital. Group 1 elements have the general electronic configuration ends, while Group 2 elements have the configuration ends. Since the outermost electrons determine how an atom behaves during chemical reactions, the presence of one or two electrons in the s orbital gives all s-block elements a number of common characteristics. One of the most important characteristics of s-block elements is their metallic character. All s-block elements, except hydrogen, are metals. They have a shiny, silvery appearance known as metallic luster when freshly cut. Their atoms are arranged in a regular crystal structure, giving them the typical properties of metals. However, because these metals react quickly with oxygen and moisture in the air, their shiny surfaces soon become dull as a thin layer of oxide forms. To prevent this, alkali metals such as sodium and potassium are usually stored under kerosene or mineral oil, where they remain protected from air and water. Another important property is their low ionization energy. Ionization energy is the amount of energy required to remove an electron from an isolated atom in the gaseous state. S-block elements have very low ionization energies because their valence electrons are located far from the nucleus and are only weakly attracted to it. The attraction between the nucleus and the outermost electrons is reduced by the presence of inner electron shells, a phenomenon called the shielding effect. As a result, the outermost electrons can be removed easily with relatively little energy. Group 1 elements lose one electron to form M-ions, while Group 2 elements lose two electrons to form M-ions. Because they lose electrons so easily, S-block elements exhibit high chemical reactivity. They react readily with water, oxygen, halogens, acids, and many other substances. Group 1 elements are especially reactive because they need to lose only one valence electron to achieve a stable noble gas configuration. Group 2 elements are also reactive but are slightly less reactive because they must lose two electrons instead of one. For example, sodium reacts violently with cold water to produce sodium hydroxide and hydrogen gas, while magnesium reacts much more slowly with cold water and more readily with hot water or steam. As we move downward in both groups, reactivity generally increases because the outermost electrons become farther from the nucleus and are removed more easily. S-block elements also have low electronegativity. Electronegativity is the ability of an atom to attract shared electrons toward itself during the formation of a chemical bond. Since S-block elements lose electrons easily rather than attract them, they have very low electronegativity values. This means they prefer to donate electrons instead of sharing them strongly. As a result, they usually form ionic compounds rather than covalent compounds. For example, sodium transfers one electron to chlorine to form sodium chloride, while calcium transfers two electrons to oxygen to form calcium oxide. The positive ions formed by S-block elements combine with negative ions to produce stable ionic compounds. One of the most noticeable physical properties of Group 1 elements is their soft nature. Alkali metals such as lithium, sodium, and potassium are so soft that they can often be cut with an ordinary knife. Their softness is due to the relatively weak metallic bonding between the atoms, since each atom contributes only one valence electron to metallic bonding. The attraction holding the atoms together is not very strong. As we move down Group 1, the atoms become larger, metallic bonding becomes weaker, and the metals become even softer. Group 2 elements are generally harder than Group 1 because each atom contributes two valence electrons to metallic bonding, creating a stronger attraction between the atoms. Another important characteristic of S-block elements is their good electrical conductivity. Metals conduct electricity because they contain free-moving or delocalized electrons that can move easily throughout the metallic crystal structure. In S-block metals, the valence electrons are loosely held and can move freely when an electric field is applied. These moving electrons carry electric charge through the metal, making S-block elements excellent conductors of electricity. This property is why metals such as magnesium and calcium are widely used in electrical and industrial applications. In addition to conducting electricity, S-block elements are also good conductors of heat. Heat energy is transferred through metals by the rapid movement of free electrons and the vibration of atoms in the crystal lattice. Because S-block elements possess mobile valence electrons, thermal energy can move quickly from one part of the metal to another. This property makes these metals useful wherever efficient heat transfer is required. S-block elements are also known for their strong reducing power. A reducing agent is a substance that donates electrons to another substance during a chemical reaction. Since S-block elements lose electrons very easily, they readily donate these electrons to other atoms or ions. When an S-block metal loses electrons, it becomes oxidized, while the other substance gains those electrons and becomes reduced. For example, sodium changes from Na to Na by losing one electron, while magnesium changes from Mag to Mg by losing two electrons. Because they readily donate electrons, S-block elements are considered powerful reducing agents. The flow diagram in the image summarizes the chemical behavior of S-block elements in a simple sequence. First, S-block elements possess one or two valence electrons. Because these electrons are loosely held, they are easily lost during chemical reactions. The loss of electrons results in the formation of positive ions such as M or M. This easy electron loss explains their high reactivity and also makes them strong reducing agents. Nearly all of the chemical properties of S-block elements can be understood by following this sequence. The image also compares the behavior of Group 1 and Group 2 elements. Group 1 elements are described as very soft and extremely reactive because they contain only one valence electron, which is removed very easily. Their reactions with water are often vigorous and may even produce flames or explosions. In contrast, Group 2 elements are harder and less reactive because removing two electrons requires more energy than removing one. Their reactions are generally slower and easier to control. Nevertheless, both groups exhibit similar chemical behavior because they belong to the same block of the periodic table. Another shared characteristic is that S-block elements usually form basic oxides and hydroxides. When these metals react with oxygen, they produce metal oxides, and when these oxides react with water, they form hydroxides that produce alkaline solutions. This is why Group 1 metals are called alkali metals, and Group 2 metals are called alkaline earth metals. Their hydroxides increase the concentration of hydroxide ions in water, making the solution strongly basic. S-block elements also have large atomic radii compared with many other elements in the same period. Their valence electrons are located relatively far from the nucleus, making electron removal easier. As we move down each group, additional electron shells are added, increasing the atomic size. The increasing distance between the nucleus and the valence electrons reduces the attractive force, leading to lower ionization energy and higher reactivity. Because of their high reactivity, S-block elements are never found in the free state in nature. Instead, they exist as compounds such as chlorides, carbonates, sulfates, nitrates, silicates, and oxides. Sodium occurs naturally in rock salt, calcium is found in limestone, magnesium is present in seawater and minerals, and potassium is abundant in various mineral deposits. Their tendency to react quickly with other elements prevents them from existing as pure metals under natural conditions. S-block elements play essential roles in everyday life and biological systems. Sodium and potassium ions are vital for nerve impulse transmission and muscle contraction. Magnesium is the central atom in chlorophyll, making photosynthesis possible in plants. Calcium is essential for healthy bones and teeth and also participates in blood clotting and muscle function. These examples show that, despite their high reactivity, S-block elements are indispensable for both industry and living organisms. The common characteristics of S-block elements arise from the presence of one or two valence electrons in the outermost s orbital. They are metallic, possess low ionization energy and low electronegativity, lose electrons easily, form positive ions, conduct heat and electricity efficiently, act as strong reducing agents, and exhibit high chemical reactivity. Group 1 elements are generally softer and more reactive, while Group 2 elements are harder and moderately reactive. Understanding these shared properties provides the foundation for studying the chemistry of the S-block, and explains why all members of these two groups behave in such similar ways despite differences in their size and atomic mass. One of the most noticeable physical properties of Group 1 alkali metals is that they are extremely soft. In fact, these metals are so soft that they can easily be cut with an ordinary knife. This is a very unusual property because when we think of metals, we usually imagine hard and strong materials such as iron, steel, or copper. However, alkali metals behave very differently. If you place a piece of sodium or potassium on a table and carefully cut it with a knife under proper laboratory conditions, it will slice easily, almost like cutting wax or hard butter. When the metal is freshly cut, the surface appears bright and shiny with a beautiful silvery metallic luster. However, this shiny surface quickly becomes dull because the freshly exposed metal reacts rapidly with oxygen and moisture present in the air, forming a thin layer of oxide on its surface. The softness of alkali metals is directly related to their electronic configuration, which is Ns. Every Group 1 element has only one valence electron in its outermost shell. This single valence electron participates in metallic bonding, the type of bonding that holds metal atoms together. Metallic bonding occurs because positively charged metal ions are surrounded by a sea of free-moving or delocalized electrons. These mobile electrons attract the positively charged metal ions, holding the entire metallic structure together. The strength of a metal depends largely on the strength of these metallic bonds. Since each Group 1 atom contributes only one valence electron to the metallic bond, the attractive force between the metal ions and the electron cloud is relatively weak. Because the metallic bonds are weak, the atoms can slide past one another easily when pressure is applied. This weak attraction makes the metal soft and easy to cut. In contrast, many other metals contribute 2, 3, or even more valence electrons to metallic bonding. More delocalized electrons produce stronger electrostatic attractions between the positive ions and the electron cloud, resulting in much harder metals. The image explains this concept by stating that alkali metals have weak metallic bonding because every atom contributes only one valence electron. Since only one electron is available to hold the crystal structure together, the attraction between neighboring atoms is much weaker than in harder metals. This weak bonding is the primary reason why sodium and potassium are much softer than metals like iron or aluminum. Another reason for the softness of alkali metals is their large atomic size. As we move down Group 1, each successive element contains one additional electron shell. This increases the distance between neighboring atomic nuclei and the delocalized electrons that create metallic bonds. The greater this distance becomes, the weaker the attractive force between the positive metal ions and the free electrons. Consequently, metallic bonding becomes weaker as atomic size increases. The image clearly shows this trend with the statement, larger atomic size, weaker metallic bonding, softer metal. This relationship explains why the softness of alkali metals increases as we move down the group. Lithium is the hardest member of Group 1, sodium is softer than lithium, potassium is softer than sodium, rubidium is softer than potassium, cesium is even softer, and francium is expected to be the softest member, although it is extremely rare and highly radioactive, making direct study very difficult. The image compares sodium and potassium to demonstrate this trend. Both metals can be cut easily with a knife, but potassium is even softer than sodium. Sodium has a melting point of approximately 97.8 C, while potassium melts at about 63.5 C. The lower melting point of potassium indicates weaker metallic bonding, which also explains why potassium is softer. Since the atoms are held together less strongly, less energy is required both to separate the atoms during melting and to deform or cut the metal. The image also compares alkali metals with iron. Iron is shown as a hard metal that cannot be cut with an ordinary knife. This difference arises because iron has much stronger metallic bonding than sodium or potassium. Iron contributes more electrons to metallic bonding and has a much denser atomic structure, producing stronger attractions between atoms. As a result, iron is hard, strong, and difficult to deform, whereas sodium and potassium are soft and can be sliced with little effort. Another factor contributing to the softness of alkali metals is their low density. Density is the mass of a substance per unit volume. Alkali metals have relatively low densities because their atoms are large and are not packed together very tightly within the crystal structure. The greater spacing between atoms reduces the packing efficiency of the metal. Lower packing efficiency means weaker interactions between neighboring atoms, which further contributes to the softness of these metals. The crystal structure of alkali metals also plays an important role. Most Group 1 metals possess a body-centered cubic crystal structure. In this arrangement, atoms are not packed as closely as they are in some other metallic crystal structures. The relatively large distances between neighboring atoms and the lower coordination number reduce the overall strength of metallic bonding. As a result, the crystal structure can be deformed more easily when force is applied, making the metals softer. The softness of alkali metals is also reflected in their low melting and boiling points. Since metallic bonds are relatively weak, only a small amount of heat energy is needed to overcome these attractions. Therefore, alkali metals generally have much lower melting and boiling points than most other metals. For example, sodium melts at about 97.8 C, potassium melts at approximately 63.5 C, rubidium melts at around 39 C, and cesium melts at only about 28.5 C, which is close to room temperature. This gradual decrease in melting point as we move down the group further confirms that metallic bonding becomes progressively weaker. Because alkali metals are extremely soft and highly reactive, they require special methods of handling and storage. They should never be handled with bare hands because moisture from the skin can react with the metal. They are usually stored under kerosene or mineral oil to protect them from oxygen and water vapor in the air. If left exposed, the freshly cut surface quickly reacts with oxygen, losing its shiny appearance and forming oxide layers. The softness of alkali metals also influences their industrial applications. Since these metals are highly reactive and mechanically weak, they are generally not used for making structural materials or construction components. Instead, they are mainly used because of their chemical properties rather than their mechanical strength. Sodium compounds are widely used in industry, potassium compounds are important fertilizers, and lithium is extensively used in rechargeable batteries because of its light weight and high electrochemical potential. It is important to remember that softness is primarily a characteristic of Group 1 elements. Group 2 elements, known as the alkaline earth metals, are noticeably harder. This is because each Group 2 atom contributes 2 valence electrons to metallic bonding instead of 1. The additional electron strengthens the electrostatic attraction between the metal ions and the electron cloud, producing stronger metallic bonds. Consequently, Group 2 metals such as magnesium and calcium are harder, denser, and possess higher melting points than the alkali metals. As we move downward through Group 1, the increase in atomic size causes the outermost electrons to become farther from the nucleus. The larger distance weakens metallic bonding even further, making the metals progressively softer. Therefore, the general trend in Group 1 is lithium, sodium, potassium, rubidium, cesium, francium hardness decreases, while softness increases. This trend is summarized in the image by the statement softness increases down Group 1 because metallic bonding becomes weaker as atomic size increases. This simple relationship connects atomic structure with physical properties and helps explain why larger alkali metal atoms form increasingly softer metals. The extraordinary softness of alkali metals is a direct consequence of their ends electronic configuration, weak metallic bonding, large atomic size, low density, and body-centered cubic crystal structure. Each atom contributes only one valence electron to metallic bonding, producing relatively weak attractions between neighboring atoms. As atomic size increases down the group, metallic bonding becomes even weaker, making the metals progressively softer. This is why sodium and potassium can be cut easily with an ordinary knife, while hard metals such as iron remain difficult to cut. Understanding these structural and electronic factors provides a complete explanation of why Group 1 alkali metals are among the softest metals found in the periodic table.